This problem is a lot like one that we just worked in a different video, which is, again, a block on an incline and a hanging mass over a pulley like that. The difference in this particular problem here is that there's going to be friction in here now. And so I've started the problem out a little bit here, just some of the steps you can find worked in detail in the other video here. We've got some of the forces labeled on here. Let's get a few signs in here. This is sort of a downwards mg, because what I call down negative. Looks like my pen's dying here. Something like that. And the upwards T will be positive like that. Opposite tensions on the ropes have opposite signs on the opposite ends, that is, so that'll be a negative right there. And the frictional force will be positive. Now, the reason why I knew the frictional force is going to be drawn the way it is right here is because there must be some indication of the problem, and there has to be. I'm not just making this up. You must read through the problem and find some indication of which direction the system's moving. So in this case here, I'm just sort of saying that somewhere in the problem it told us that M2 is, say, moving up the incline. Could have been down the incline, but I'm just saying it was up the incline. If that's true, since friction always opposes motion, if V is up the incline, friction must be down the incline. That's why I have this big red arrow drawn in here like that, and I have it labeled positive, opposite sign to the T, because it's down the incline for the friction. And that's sort of the force on the problem, but there's one more in here which you have to be very careful, and this is probably one of the first problems where you'd very easy to forget about it because of all the other stuff going on with the friction and stuff. So even though there's friction, even though there's tension and pulleys and the other hanging mass, this mass M2 is still on an incline. It still has a natural tendency to want to slide down the incline, so I must not forget that there is also going to be a sliding force on this block, which was covered in a couple of other problems where it comes from. And the sliding force, since it's down the incline with friction, is also going to have a positive sign like that. So this is where the problems start to become a bit complicated, and you can easily get sort of messed up if you don't recognize and remember all your forces and stuff. So what we'll do then is we have all the forces and the signs now. Let's just apply Newton's laws and see where we get. So for mass M1, that's the hanging one right here, nothing much is going to change for that one. Again, there's no x forces, so we won't even bother with equation 1, even though it's there and valid, but we can't get an ace of y out of that. It'll be the sum of the forces divided by m. I see a plus t minus an m1g over m1. And I can put a big box around that and go, hey, there you go. I've gotten an acceleration already for the hanging mass. And you'll notice for the last couple of problems that it hasn't changed at all, because this mass here hanging by this rope doesn't really realize what could possibly be over here. So this generally just stays the same throughout. But now M2 is the big different one, so let's see what we get there. Once again, like we covered in another problem, we have this funny slanted block now, and the coordinate system might be a little vague, but we'll call this the y-axis and this the x-axis. That'll sort of be the way we're going to orient ourselves. Something like that, okay? So we'll just get right into it then. If we look along the x-axis now, a sub x then is going to be, well, what do I have on the x-axis? I have a tension up, a sliding force, and friction down. So I get minus t plus the sliding force plus friction. And if I divide all of that by m2, that's essentially the core of an x acceleration equation for the block on the incline. And again, the x-axis is the axis along the incline like that, so that's why I'm calling it x. So off you go. We need to start filling some stuff in now because there's a bunch of incomplete variables in this particular problem. In particular, what is the sliding force and what is friction? Now we know a few things from some other problems you can catch in some other videos here that we have posted. You know that the sliding force is always going to be m2, or whatever the mass of the object is, times g times the sine of the slope of the angle. There you go. There's the sliding force. And we also know that the frictional force is equal to mu times the normal force. So the reason why I'm focusing on these is because I have those variables explicitly written out right there and right there, and I need to fill something in for them. So F sub s, the sliding force, is ready to go. That's ready to fill in. But now we need the normal force so we know what to fill in for friction. The normal force comes from backing up back to the original problem and seeing if we can figure a couple things out here. We know that this object is sitting on an incline, so there will be a normal force on it just like that. There's your capital N. And we know this mass also has its weight straight down, so there'll be an m2g straight down. The way we can figure out the normal force then is by recognizing that this object never lifts off the surface, nor does it dig into the surface. It always sits on the surface. So we can conclude then that the acceleration of this block along this y-axis is equal to 0. That'll hold it on there, given that the velocity is equal to 0. But the problem, again, never said anything about this block leaving the surface or digging into it, so we can probably assume that the velocity along that axis is equal to 0. So the way I'll do that then is I'll break this gravity up into a couple components right here. This component here, which is mg times the cosine theta, and this component over here, which is the sliding force, which is mg, I'll have to put it over here, times the sine of theta. Getting a bit crowded in there, but hopefully if you're following along you got that. So So once again, I draw this little right triangle underneath the gravity vector, underneath the block, and if this is theta, that's going to be theta right in there. And it's kind of small here, but this is the adjacent side involving the cosine, this is the opposite side involving the sine. And so if I look at it very carefully now, if I go back to this sort of analysis here and go, okay, well on the block here, I want AY to be equal to 0, so the thing will never levitate, but AY is the sum of the Y forces divided by the mass. So I have a normal force up, and I have a minus m2g times the cosine of theta down, and all that's going to be divided by m2. So this equation right here is this application of Newton's law, but I put a sub y equal to 0 because that block never levitates or digs into the surface. And if I just solve this thing directly now, because it's equal to 0, the normal force pops right out, m2g times the cosine of theta, and there's my normal force. So now I'm in a position to be able to form what my friction is equal to. It's mu times m2g times the cosine of theta. And put a big box around that. There's your friction. Okay, so the reason why I went through all that work now is because I have this equation for the x acceleration of the block on the incline, and now I know what to fill in for the sliding force and for friction. Let's just do it and see what the equation comes out to be. It gets to be a little long, but I think we can write it sort of down here at the bottom. In particular, I'll get that the x acceleration on the block is minus t plus m2g times the sine of theta. There's the sliding force right there. Plus mu m2g times the cosine of theta. I guess the equation is a bit long there, but anyway, that's what the top looks like. Minus t plus m2g sine theta, that's the sliding force, plus mu m2g cosine theta, that's the frictional force. They have the same signs because they're in the same direction, and there's that minus t trying to pull up the incline, and you can divide that whole thing by m2, because we're still talking about mass m2. You can put a big old box around this because it's quite an accomplishment and quite a progress towards the core of the problem here. You have a full-out expression for the acceleration of this mass along that incline right there. There you go, a sub x. Now what you do is, like in some other problems, apply a bit of common sense. This x acceleration that we just solved for is the same as the y acceleration for this mass because the masses are connected by ropes. So you can look back at some of these equations you formed here. This one, which you formed very early on in the problem-solving process and probably forgot about, this AY right here, the y acceleration of the hanging block, is exactly the same as this AX right here because the two objects are linked by ropes. So I will try to bring all these together to show you the big result. In fact, I think I'll do it right here in the center. I'm going to erase all of this stuff in the center to give me a little room, and recognizing that that y acceleration of the hanging mass is equal to the x acceleration of the mass on the table, I'm going to set this equation equal to that one, and I'll get one big equation which will be my core answer. So plus t minus m1g over m1 is equal to minus t plus m2g sine theta plus mu m2g cosine theta. Almost out of room, all that divided by m2. Wow. What a really big equation. Kind of nasty and long, but you put a big box around it and you're essentially done with this problem. And why are you done? You certainly couldn't turn anything like this in for an exam or a solution or something, but if you look at it very carefully and crank up your algebra, the only variable in here that's something that you'd like to solve for is t. The m1s and the g's and things and the thetas, likely you'll know in the problem, so you could definitely use some algebra here to solve this for t. And I'll just go ahead and leave that up to you to do that. So that's sort of the first thing you could do in terms of like getting this problem solved once and for all. And the second thing you can do is once you know what t is here, once you know the tension in the rope, you can take that t that you just found, this one right here, and plug it in for either t right there or the t right here, and that'll allow you to solve for a. This is probably the simpler equation right here, so we can just put it in for there. So my claim is that once you know the t, you can return to either one of these constituent equations, either this one or this big long one right down there, to get a. And t and a are usually what these types of problems are asking for, so you can get your tension and your acceleration. The other way you could do this, just to be a little bit cleaner about it, if you're so motivated, you're trying to organize these thoughts in your head, is remember we started this premise here by saying that ay and ax are the same number. So you could return to your equations and sort of just rewrite them and say all of this business here is just equal to a, and sort of think about it like a whole other equation. And all of this business down here is also just equal to, I don't even know where to write it in here. All this would just be equal to a equals, and you can put a big box around that and say that's a whole other equation right there. And where the a's come from, again, it's that logic that the acceleration of the hanging mass is equal to the acceleration of the mass on the surface. They have to have the same acceleration because they're tied together by a rope. So I'm just sort of saying that AY here and AX down here are all equal to the same A, and off you go. Either way, good luck with that algebra.